jump into the introduction. This is the lake of Section 7 in Shah Alam. We specifically selected this Tasik Section 7 as our case study because it is represent as common real-world problems. Nature rarely gives us a perfect shapes, right? Unlike a swimming pool, which might be perfect rectangle, this lake has highly irregular curved shoreline. Consequently, we cannot rely on standard geometric formula like pi r square or simple length times width calculations. Instead, we had to apply numerical methods to translate this physical irregular landform into a precise mathematical model. Next, we're gonna go to problem statement and object. Irregularity leads directly to our problem statement. While we can easily view the lake on Google Maps or a printed grid, these are essentially just static images. They do not provide us with a mathematical function that we can analyze or calculate. Without a defined function, we are unable to perform calculus operations to find the exact area. So, to solve this, our project was guided by three main objectives. First, we aim to construct polynomial equations that accurately trace the lake's boundary based on specific coordinates points. Second, we utilize defined integration on this derived equation to mathematically calculate the total surface area enclosed by the shoreline. The third one, we sought to validate our numerical model. We did this by comparing our calculated results against the graphical methods, which is manually counting unit squares on grid paper to quantify the accuracy of our approach.
Next, we will see the scope and limitation. This study applies Newton's forward divide difference interpolation method to estimate the surface area of Tasik Section 7 Shah Alam. The scope of this study is limited to the use of discrete coordinate data point that obtained along the boundary of the lake. Using this data point, an interpolating polynomial is constructed to approximate the shape of the lake boundaries. And this polynomial is subsequently used to estimate the area of the lake. However, several limitations are present in this study, which is the accuracy of the estimated area depends strongly on the number and quality of the selected data. Since the Newton forward method assumes equal spacing between points, any slight inconsistency in spacing may lead to interpolation error. In addition, the actual boundary of the lake is complex and irregular, and the interpolating polynomial can only provide an approximation rather than exact representation. Next, we will see the methodology and implementation. On the graph paper, the lake was divided into 6 subregions that are assumed to be equal in size. Next, 4 coordinate points that lie on the lake boundary were plotted for each subregion. And next, the plotted points were transferred into the finite divided difference table, and Newton forward method was applied to complete the value in the table. Using the value obtained, a mathematical equation was formed using Newton forward divide difference interpolation formula, and the equation was integrated to find the area of each subregion. Next, step 2 to 4 were repeated to all 6 subregions. And last, the total area of Tasik Section 7 was calculated by summing up all the sub-region areas.
Now let us dive into the results, which calculates the area. After successfully deriving the polynomial equations for all 6 regions of the lake, we proceeded to the calculation phase using definite integration. If you look at the table on the slide, you will notice that the integration results for each specific region is interesting. We have region B, C, and D yield negative area values. I want to assure you that this is mathematically correct and expected. Since the lake forms a closed loop, the integration direction in this region runs backwards relative to the x-axis. These negative integrals effectively subtracts the empty space beneath the lake's lower boundary, ensuring that we are left with only the net area in the lake itself. So, when we algebraically sum these positive and negatives area, we arrive at a final total calculate area of 2,897.72 unit squares. Next, we're gonna move to error analysis and real scale. Finally, we move to error analysis. To determine how reliability our mathematical model actually is, we compared our calculated results to 2,897 units against the benchmark of manual grid count method, which yield 4,045 units. This comparison resulted in percentage relative error of 28.37%. So, why the discrepancy? This error largely highlighted that trade-off between resolution and approximation. The manual grid count is tedious but captures every tiny detail and hands down map. In contrast, Newton's method generally smooth and continuous curve. Essentially, the polynomial smoothed out the sharp, irregular edges of the shoreline, which led to a slightly smaller calculated area. It is also crucial to translate this into a real-world scale. Based on our map scale, 1 unit square on the graph corresponds to 25 square meters in reality. This means that while our mathematical model estimated that lake size at approximate 72,000 square meters, the manual count suggests it is closer to 101,000 square meters. This confirms that while our method is logically sound, a higher number of data points would be needed to capture those finer details. Next, we're going to proceed with
And for the last is conclusion. What we can conclude is Newton forward difference method can be used to estimate the area of irregular shape such as Tasik section 7. The method converts discrete data into a continuous mathematical model that can be integrated. Difference from the graphical methods are mainly due to polynomial smoothing of irregular boundaries. Although less precious than manual grid counting, the numerical method is faster and more scalable. This study also highlights the practical application of numerical methods in real-world problems.